So we're going to talk about something called phase diagrams. And a phase diagram describes the relationship of pressure and temperature to the state. So the way they plot a phase diagram is put pressure on the y-axis and temperature on the x-axis. And then they say, let's say you pick a temperature and pressure. Let's say it's for H2O, and let's you say it's 1 atmosphere and it's 75 degrees Celsius, right? What's the state? Well, at those states, it would be a liquid, so it gets graphed as a liquid. And then when you graph that point, then you have to look at other points. So they just look at all the points, and you generate a graph that looks something like this for water. Okay. So, and I'll go back to some the rest of the description of that slide, but let's say you're at 75 degrees and 1 atmosphere, so you would be a liquid. But then if you got to 0 degrees Celsius here, that's when water freezes. And so we have over here all the solid state. So this line represents the relationship between freezing point and pressure. And then this line is the vapor pressure curve. Okay. This is the sublimation curve going from the solid to the gas. So for example, if you're at this temperature and pressure and you increase the temperature, at this point you'll be transforming into the gas phase from the solid state. So there are lines that these lines represent the state changes. There is something called a critical point, and we'll spend a little bit of time talking about the critical point. But you'll notice that it's the phase transition between liquid and gas, and then it stops. So what this implies is that above this temperature, there's no longer a definite boundary between the liquid state and the gas state. That is, we're into a new kind of material, which we call a supercritical fluid, which has some interesting properties. So we'll get back to it. Then there's something called the triple point. So think about this, right? This point is the temperature at which water boils at 1 atmosphere. But what this says, and this is what we talked about before, if you lower the applied pressure, you lower the boiling point, right? Turns out you also, at that same instance, are changing the freezing temperature, the freezing point of ice. It actually gets higher at lower pressure, which is unusual. Water is the only substance that has this line going in the backwards direction. So what do you see at this point? Well, you would see boiling water at this point. What do you see at this point? Well, you see boiling water here too, because that's the phase transition for this temperature. But here, this is the unusual point. It's called the triple point. And it's actually when all three states of matter are in equilibrium with each other. In other words, you're going to see boiling water and ice at the same time at this particular value, okay? Okay, so for most substances, like I was saying, the freezing point increases as the pressure increases. The additional pressure helps to fuse the liquid into the solid. Ice is one of the only substances, like I said, that has a curve that shoots backwards, which means if you increase the pressure, its freezing point gets lower. Okay. Oop, wrong way. So freezing point increases as pressure increases. So usually it goes this way. Increasing pressure makes it easier to freeze. For water, it gets harder to freeze. And we'll talk a little bit about water's structure as a solid to understand that. All right. So let's talk about the critical point. If you heat a liquid to its critical temperature, it can no longer be a liquid. And the result is it creates something called a supercritical fluid. This is what the liquid gas state looks like this is for carbon dioxide, I believe. And what we're doing is we're increasing the temperature. So you actually see a little bit of boiling going on here. And then you'll notice as you reach the critical temperature, you notice what happens is you have this weird boundary. No longer do you have a clear definition between liquid and the gas. The boundary becomes cloudy, and then eventually it becomes one phase. Now, it's kind of like a gas, okay, in that it has the properties of a gas that allow it to expand to fill its container. But at the same time, because um, there was a liquid down here, the density is much higher than that of the gas. So normally the density between here and here is about a factor of about 1,000. That is, the liquid's about 1,000 times more dense than the gas. But typically in a supercritical fluid, the factor is only 2 or 3. It depends really on the size of the container that you're using. But in this case, if you're saying that you're doubling the container, the density is only of the supercritical fluid is only half that. But it has the same fluid properties as a gas. This is in fact how they extract caffeine from a lot of coffee beans. The fancy way to do it is use supercritical carbon dioxide. It's capable of dissolving caffeine, and then they extract the beans with supercritical carbon dioxide. Then they separate the beans from the supercritical fluid. They allow the supercritical fluid to return back to the gas state, and all the solids will precipitate out of it, which they can collect. That includes the caffeine. And then they save the fractions of the solid that add to the flavor, I think, and they add those things back in. But anyways, yeah, supercritical fluids are very interesting all in themselves, because of their properties being like both liquids and gases. So you need to be able to navigate within a phase diagram and sort of understand in a conceptual sense what transitions you'll see as you make certain changes. So for example, if I said if you start at minus 25 degrees Celsius with H2O and you go to 125 degrees Celsius at a pressure of 1 atmosphere, what do you expect to see? Right? Well, you should be able to think to yourself, well, at 1 atmosphere from minus 25 I should see a solid, and then at 0 I should see the fusion of the ice to the liquid, right? So I'll see the ice melting, and then I'll be heating the liquid all the way up to its boiling point at 100 degrees C, at which point I will see boiling water. And then after that point, I'll just see the gas, okay? So now, that should be common. That should be familiar to you because that's what we did in the problem when we did the heating curve, right? But what happens if you're under some other conditions? One of the things you should recognize that this line, the slope of it's not very steep. So you don't usually see much change there. So if you're at minus 25, right, and you're at this pressure, whatever it happens to be, right, and it turns out this scale is not linear. So let's say we're here, and this is not necessarily half an atmosphere, even though it looks like it might be. And you heat it from minus 25 to 100, what do you expect to see, right? Well, you would still expect to see near the normal freezing point for ice, the ice melting, becoming a liquid, and then at some temperature substantially less than the boiling point, what you would see is the vaporization or the boiling of the liquid and then converting into the gas phase. So you would know, because you understand that vapor pressure and applied pressure, right? The relationship is when the vapor pressure equals the applied pressure, that the liquid boils, that if the applied pressure is lower, it's going to boil at a lower temperature. You may not be able to specifically say what the temperature is, but you should still have a good idea. Okay, so this is one for you to think about for a little bit, this next one. What happens when you're starting at a temperature of 25 degrees and 1 atmosphere, right? What do you see happening when you decrease the pressure but maintain a constant temperature, right? So what would you see? Well, as you decrease the pressure, what's happening is the boiling point of the liquid is decreasing, right? So at some point, as you're going down in pressure, you will eventually see the liquid boil. You can in fact get water to boil in a container by pulling a vacuum on it and getting the liquid to boil because you decrease the applied pressure. So you would say at 25 degrees Celsius we would see liquid water, and then as we lowered the pressure, eventually the water would boil and then convert into the gas phase. So take a look at these two lines, A for iodine and B for carbon dioxide, and describe what you see when you go from 1 atmosphere to something like 90 atmospheres, right? Now you're given the phase diagram, right? So what do you expect to see? So at this point here, we're starting with liquid iodine. And as I increase the pressure, it freezes, right, as the pressure reaches this point here, and then eventually all converts to solid. So increasing the pressure causes the freezing of the solid as you on this line as you go from 1 atmosphere to something like looks like must be close to 100 atmospheres. Oh yeah, I think that is 100 atmospheres on that mark. What happens for carbon dioxide, right, when you're starting at below 78 degrees Celsius and going to something like, it looks like it might be about minus 60 degrees Celsius. The scales aren't linear, so it's a little difficult to tell. In this graph, what do you think what would happen, right? And then you should be able to say, well, it'll be a solid, right? And as I increase the temperature at 1 atmosphere, then what happens is I would see the sublimation, because I'm going to the gas state, sublimation of the carbon dioxide, and then eventually it'll completely convert to the gas state. So think about what the phases are. In general, if you'll notice, solid, liquid, gas. So the V in the middle contains the liquid, and then the left of it at lower temperatures the solid, and to the right is the gas. Here's another variation of that same problem. A substance has a triple point at minus 25 degrees Celsius and 225 millimeters of mercury. What is most likely to happen to a solid sample of substance when it's warmed from minus 35 to 0 degrees Celsius at a pressure of 220 millimeters of mercury? And then they give us some options. The solid melts to the liquid, the solid sublimes to a gas, and then nothing. The solid remains solid, right? So how do you answer this question? And it's not conceptually that simple. What you need to do is you need to set up the phase diagram and sketch it out, and then look at where the transition is on the phase diagram. So the easiest thing for me has always been to just draw it. And then I have a triple point. This is my triple point, and it says minus 24.5 degrees Celsius. So this is minus 24.5 degrees Celsius. And then the pressure is 225 millimeters of mercury. Now this is a triple point, so I expect there to be one line coming off the triple point here, and then I expect this line to be going up mostly vertically. Something like that. Usually they go to the right, and then this is the vapor pressure curve, so it has this shape, okay? So I've defined points on my graph really just based on the triple point. Now we're at minus 35 degrees Celsius, right? So that's over here somewhere to the left of this line. And I'm at a pressure of 220 millimeters of mercury, so I'm underneath the triple point. So I'm going to heat this and go from here along this line in this direction until I get to 0 degrees Celsius. So what do you see, right? Like in the earlier examples, the phase diagram was given to you. Now we've sort of drawn our own. We know the triple point's at 225. We know we're at 220. So when we go across, at some point, right, we're going to see the solid convert directly to the gas or sublime to the gas. So the answer for this one would be B, like that. But again, conceptually, these are hard to do. Like you have to see the whole phase diagram. And so it's easier just to sit down and draw it. Use the information that's given, right? This is the, and then remember solid, liquid, and gas states. And then based on what you're given, try to determine what phase changes you'd see. So for example, if it was at 225 degrees or 230 millimeters of mercury, you know you'd be above the triple point. So as you went across, for sure you would see the liquid formed. But depending on the curvature of this line, you might also see the gas, but some additional information might be given or the answers would have to be slightly different. Okay. So hopefully that helps you with the phase diagrams. I have one other slide that I should have put in earlier, but I wanted to summarize real quickly the properties and the effects of intermolecular forces. So if we're looking, these are the properties, right? Boiling point. If you increase the intermolecular force, we know the boiling points increase, the melting point increases, viscosity increases, and surface tension increases. And we can explain that simply by the stronger attraction of the molecules. For example, making it harder for them to leave the liquid state, or making them harder to leave the solid state, so the melting point goes up, or harder to move about, or harder to spread apart. On the other hand, the vapor pressure goes down as the intermolecular force goes up. And so we also think about like the vapor pressure and the boiling point being tied together, and we think about the vapor pressure curves when we're doing that. And then finally, there's the effect of temperature on the intermolecular forces. Boiling point and melting point are generally not that temperature dependent, but viscosity and surface tension both decrease as you increase temperature, and decrease as you increase temperature, and vapor pressure increases as the molecules get more kinetic energy and more of them can leave to create the gas phase, so increases the rate of evaporation.